Hi everyone. So today we will learn about why we need to use the partial derivative method when we want to optimizing the home insulation. So the first reason is many factors affect insulation at the same time. Home insulation depends on more than one variable such as wall thickness, material type, and window size. Partial derivative help us study each factor one by one while keeping the others fixed. Secondly, is about the find the best combination. We want the best mix of material, thickness, and cost to reduce heat loss. Partial derivative help us to calculate the exact value that give the lowest heat loss or cost. Last one is about why we need to use the partial derivative method is because of the real world problems are not one-dimensional. In real life, changing one part like roof insulation may affect the whole system. Partial derivative help us handle this complex, multivariables situation with accurate results. So here is about why we need to use the multiple integral method when we want to calculating the solar energy harvesting. So the first reason is about solar energy is spread over an area. Solar panels collect sunlight over a surface like roof. A single integral only works along a line one dimension, but we need to calculate energy over a 2D area. So we need to use the double integrals. So the second reason why we need to use the multiple integral method is about more accurate and realistic results. In real life, solar energy depends on both position and time. If we want to include how sunlight changes throughout the day and how different parts of the panel receive energy, we need to use the double or triple integrals to get the total energy collected in a precise way.
Let's start with a practical problem optimizing home insulation. A family wants to reduce their heat costs, so they need to find the best thickness for their wall insulation. This problem is modeled using Fourier's law, which describes how heat flows through materials. Using partial differential equation, we can predict heat loss and find the insulation thickness that saves the most energy.
So we are going to talk about on how to optimize home insulation by using partial differentiation. And through calculation, we are using Fourier's law of conduction. The formula says that Q equals to K A delta big T small t over by D, which Q is heat loss, K is thermal conductivity, A is the wall area, delta big T is temperature difference, small t is time, and D is insulation thickness. So moving on to the cost analysis, the insulation cost is linear with thickness, which is C equals to C1D, and energy cost is proportional to the heat loss, which is by using the Fourier's law of conduction. Therefore, the total cost would be C1D plus C2KA delta big T, T over D. Next, we are going to find the solution using partial differentiation. First, we compute the partial derivative of the total cost with respect to D by using the formula which we have discussed earlier. We partially derive it in respect to D because we want to find the optimum thickness so that we can optimizing the home insulation itself. And after that, we are going to set the derivative equals to 0. Therefore, we can find a minimization of this equation. So for conclusion, The optimal insulation thickness minimizes the total cost, balancing material and energy expenses.
Now, let's look at energy harvesting through solar panels. This family installs solar panels and wants to estimate the total energy they can produce in a day. Since solar irradiance changes with position, x, y, and time, t, we express it as a function SYT in watts per cubic meter. To find the total energy harvested, we use multiple integrals over the area and time to account for all variations in sunlight.
So I will explain about the problem 2, which is solar energy estimations. Suppose the same family installs solar panels. How can they estimate daily energy productions? Here we'll model irradiance over time and space using multiple integral. The first key component is one solar irradiance model. Irradiance I XYT varies with position XY and time, which is T. We simplify it as I XYT equal to I max sine pi T over T times 1 minus X over L. Here is I max is peak irradiance, T is daylight hour, and L is panel length. So moving on for the solution step, which is steps 1, integrate over space. First integrate First integrate 1 minus X over L across the panel area W times L. And for the second step, integrate over time. Integrate the sine function over daylight hour. So integration T0 sine pi T over T dt equal to 2T over pi. This captures the sun intensity peaking at this one is combined result. Multiply both result with I max. And final equation is E equal to I max times WL over T over 2 times 2T over pi equal to I max AT over pi, where is A equal to WL is the panel area. For example, if area is 10 meters squared, T equal to 12 hours, and I max equal to 1000 watt per meter squared, daily energy is 38 kilowatt per hour.
So here is the conclusion about our presentation. So the first conclusion is about we use partial derivative to improve home insulation because they help us to see how each factor like material or thickness affect heat loss. This helps us to choose the best way to save energy. The second conclusion is about we use multiple integrals to calculate solar energy because they help us add up the sunlight collected over a big area and time. This gives a more accurate total energy.